Hello all, I will be continuing with the bubble cap theory design, and this is the second class on the same topic. What we had concluded at the end of the last class was this: we require additional checks for entrainment, slot opening, liquid gradient on tray, downcomer backup, pressure drop across tray, and outlet wear length and height. And definitely we had to finalize the tray layout. That means where to place the vapor dispersers. To start with, we talk about the entrainment, and this entrainment check is also very similar to what we have seen. In fact, it is practically the same what you find in case of your sieve trays. It is the same plot. In fact, the same FLV factor is used, which is the ratio of the liquid to vapor mass velocities. Then you have the rho v and rho L. So, we know the value of FLV. So, if we know the x axis parameter, and we have decided on a Murphy tray efficiency for the tray to maybe 75% or rather 80%, and in case I have a FLV factor of this, the corresponding value here for my psi will be 0.12 or 0.13, something like this. That means, I know this particular expression. The entrainment quantity E in moles per hour and the moles of liquid flowing across the tray, if it is NL, the relationship in this particular case is given by this. Or in other terms, E upon NL is equal to psi upon 1 minus psi. We have just found the value of psi, which is noted from here. So, it is possible for me to know, or rather I know at this particular point, the value of E upon NL. The efficiency actual will be different from whatever has been there in this particular value, which is 80, and the change will be related by this particular expression. So, I have known the quantity which is here, I put it here, I recalculate my eta actual. That means, we find here that due to entrainment, my actual efficiency is going to be lower than what I had assumed initially. As long as it is within limit, it is fine. Say if you have assumed 80 and if you get some value like 75, 76, it is usually okay. It is obvious that we need not emphasize that with increasing psi, the efficiency fall will be more. When will the efficiency fall will be more? When will you have a higher value of psi? When you have a lower value of FLV. When will you have a lower value of FLV? When you have a lower L and high MV. It is obvious with a higher vapor flow rate, the chance of liquid being blown off is more. So, that is why you can relate and you can interpret the results that you will be getting from here. Now, we can have various type of layouts on my tray. This is the simplest. We have a single downcomer and a single pass. The flow path length is from here to here, it goes like this. We have a gradient of liquid level at this point and this point. It flows by gravity. So, naturally, the H here will be H plus delta, and if my H is here, this delta is the driving force for the liquid from this point to this point. Now, what is this? This is the gradient of liquid. When is it expected to be high? When the frictional drop is expected to be large, your delta will be high. Suppose you are dealing with a liquid which has got very low viscosity, like liquid air in a cryogenic plant. You will have a very low value of delta. So, what is done? in order to give a longer residence time, you use a reverse flow tray. You will note here that instead of having the downcomer of the upper tray discharging its liquid here, it discharges here. And the liquid from this tray goes to the tray below this through this particular point or this section of your downcomer. And quite naturally, you have a partition here and you have a baffle which allows the liquid only to come from the right side to its left, like this way. Now, there are other ways of reducing this delta. This delta depends on what? This depends on the flow path length. We also know that it depends on the viscosity. So, what we do is, in order to reduce this delta, we can split the flow into two. Here what you have is a 2-pass tray, where you have the downcomer of the upper tray discharging here, the liquid getting split into two streams. The tower diameter is, if it is d, the path of each liquid in this case is half of d. So, your flow path length has come down, and quite naturally the delta is from this point to this point. Not only the path length has come down, the flow rate has also been halved. So, quite naturally, as compared to a configuration like this, this is going to give you a much smaller delta. Now, once the liquid has come here to the extremities, they are collected and they go back this way with a central downcomer. So, what we note here is something. We have a tray with a side downcomer and the next tray is with a central downcomer. You will notice here something quite interesting. You will notice here that if you, I will just get the pen back, you will notice here that there is a small recess. That means it is not a flat, it is basically there is a recess in which it discharges. So, this is done so that you have a seal here in a better fashion. You can also split the flow path in a large diameter tower into two continued sections. In that case, what will we have? We will have the first wear here, then a stepped portion of the same tray. This is the first step, this is the second step, and a second wear here. So, what you have here is the delta in this has to drive only this much of length, and the delta here drives only this much of length. This allows reducing the flow path length, keeping the flow rate same. So, quite naturally what you can have is either this or this, depending on your choice. We in industry not only limit to 2-pass trays, we have 4-pass and higher pass trays also, but more common is a 2-pass, sometimes 4-pass trays. Like in any vapor dispersers mounted on a tray, there will be end wastage that is mentioned here. There has to be a coming zone both upstream and downstream of the flow path length, and this is the length of the wear, and this is your tower diameter. Depending on what velocity, or rather what flow rate of the liquid we have, the tray selection has to be made. Here what we do is we know that we have made some estimated tower diameter. In fact, what we have done is based on the trace spacing and the diameter, we have a cross idea of the size of the tower itself. Now, depending on the flow rate of liquid, what we do is we choose whether we are going to have a reverse flow or a cross flow or a double pass or a cascade double pass. You will notice one thing, we go for a reverse flow only when my liquid flow rate is small. That means, your delta is expectedly, when my flow rate is small, is expectedly very small. Similarly, we go for the other types when we have higher flow rates, and these are the different configurations. Now, depending on the type of configuration that we have chosen, there are certain guidelines about the different areas as a percentage of the total tower cross section, which is pi by 4 into capital D square. So, this is just a table to give you an idea, and you should have a look at these and have idea about the standard typical tower dimensions, which is here. Now, what we do is we look at the view of a double bubble cap, and it is the same thing which we have here, and all during our design, we are supposed to find out the slot opening. That means, when it operates, by how much will the liquid level here in the slot get depressed. We definitely will have to check this, and we move on with this. We have here a few slides which gives the standard design of industrial bubble caps. Normally, there are typical vendors like Glitch who will be supplying you the bubble caps that you require. If required, they will also be designing the tower for you if you use their caps. It is also possible for you to make your own cap, but it is not done very commonly until it is a small plant. Regarding the slot shape, I have said there are 3 shapes possible. One thing could be trapezoidal, sometimes you have triangular, which is uncommon, and you can have a rectangular slot also. When it is trapezoidal, this is basically b by 2 if this distance is b. The dimensions and the slot widths are given here at the top, bottom, the slot height and the shroud ring. The shroud ring typically is always 6 millimeters, 1/4 inch. The standard designs are here again for the carbon steel and alloy steel valves, and these are basically the other details which is given here, and the different area ratios are there, because these area ratios are required when you go for your design and you need to calculate your other parameters regarding the flow hydrodynamics around your bubble cap. The most common industrial cap size is 4 inch, 100 millimeters. It is usually the most popular type, and it is used in small towers as well as large towers. Normally, if you are expecting that the diameter of your tower is going to be slightly less than a meter to around 3 meters, you can try by checking with the 4 inch caps first. If you find that due to some reason or the other, if you are having poor performance, that means your efficiency is not up to the mark, you definitely will be required to re-evaluate or redesign. Smaller caps and bigger caps are also in use in the smaller and the larger diameters. If you have a smaller cap, in proportion to the cap size, it will have a larger amount of slot area. If you are using smaller caps, you will be having a more flexible arrangement of laying it out on your tray, but you will require a more number of caps. Now, smaller caps are also more easily covered by the liquid. That is something desirable because it helps mass transfer and lead to higher efficiencies. But in case of large caps, normally you have a lower pressure gradient. That means you choose whether you are what size of cap you are going to use. You normally will be starting with 4-inch caps, unless you are really working with a very large tower or a very small tower. Next comes the question of the number of caps. The caps have to be located on the active tray area, and within the active tray area also you do not have everywhere where you can locate your vapor dispersants. So basically what you have to do is you have to do your tray layout arrangement. The first thing that you do is decide on the segments. The tray segments. So you know now wherever you have the joints, you have to have the backing strip, and you cannot put your vapor dispersants there. You also have to tentatively decide, you must have decided by now, what is the downcomer location and the downcomer length, and those dimensions are already known to you. It's time for you to decide on a pitch. For p millimeter pitch, naturally you can have it either on a triangular pitch, which is the center to center distance, or you could also have it on a square pitch. So if in this case an area of P square can contain how many caps? It can contain 1/4, 1/4, 1/4, 1/4. It contains 1 cap. And in this case, the area of the triangle is half, base is P, into altitude is P sine 60 degree, which is √3/2. This is equal, this contains how many caps? This contains 1/3, this is 1/6, 1/6, 1/6, that means half a cap. So the formula of the triangular pitch number of caps per meter square and the square pitch caps per meter square are derived from this geometric analysis. The actual caps, actually I have already said that, will get reduced because you require clearance from the edge, clearance from the segment joining lines, and tray support ring fixing wherever you have, and naturally in the coming zone on the tray you cannot have your vapor dispersers located. So this is usually done by trial manually with some drafting help of course, but it is primarily a manual procedure. Now this is what I have meant here by saying that NC, which is the number of caps, is obtained graphically by drawing the tray layout. Usually what you do is you put as many caps as you can and then you start removing the caps which are inadmissible to be placed there because of fouling with something else. In order to have the layout, we need to know about the dimensions which are typically used. The first thing is a coming zone. Typically, if your diameter of the tower is below 1.5 meters, you have a coming zone of 75 millimeters, which is 3 inches. If it is more the diameter, you go for 4-inch or 100 millimeter coming zone. The perforated area is about 10 to 14% of the area. The holes are either drilled or punched, the same thing which you have learnt in case of the sieve trays. Most common type of bubble cap is round bell shaped caps. They offer lower pressure drop to the flowing liquid with trapezoidal slots. There is one advantage in the trapezoidal slots. If you look at a slot, initially the liquid level will be depressed like this when you have a low flow rate. As the flow rate increases, the area which is available for the bubble to flow out increases. here what happens is, when you have if you have a low flow rate of bubble, you have a smaller area, and this makes a stream of bubbles more uniform. So, it's sort of a self-regulating capacity that you have with trapezoidal slots. You will be using rectangular slots when you know that your capacity or the turn down ratio in this case is not going to change much. That means, you are going to operate your tray with a fairly steady and steady capacity or throughput. The shout ring, we already have said many times that it is usually 6 millimeters. The recommended skirt height is 12 to 38 millimeters. It can be designed, it can be set also, and a minimum of half inch skirt height is always kept for vapor overload, because what happens is, in case there is vapor overload, it will be coming out below your skirt. You require a higher gap if you know that there will be solid settling on your tray deck. And if you have a larger clearance from the deck, your pressure drop of the liquid in its path will be less, and you will be having a lower delta, the capital delta, which is the gradient across your tray. You can go for a rotated square pitch or a triangular pattern with P greater than 2 times DO. DO is basically your punched area. We already have seen that you can accommodate more number of bubble caps if you are going to use triangular pitch for the same area, and normally the P is 2.5 to 4 times the hole diameter, or it is 1.5 times the cap diameter. Typically, what you find is 100 millimeter caps and 125 millimeter pitch. This is most common, the first trial. The slots. The slot width typically be either will be normally 3 to 12 millimeter wide. The suitable compromise is a 6 millimeter mean slot width. The height of the slot can vary depending on the size of the cap from 12 to 50 millimeters. The recommended slot height range is 25 to 38 millimeters. 38 millimeters mean 1.5 inch. Now, what we have is basically about the typical dimensions of the cap tray internal. We have to specify the riser height. The riser height is determined by the skirt clearance and the riser slot seal. We know what the slot seals are, and the recommended riser slot seal, that the vertical distance between the top of the riser and the top of the slots, this is typically 38 mm, which is about 1.5 inches. The bubble caps may be made of 5 millimeter metal sheets, if it is just carbon steel, or it will be 3 millimeter alloy steel caps. The bubble cap material typically is 410 SS 410. Now, we have to have an idea about the optimum wear length with the segmental downcomer. The segmental downcomer, typically the length is around 60 to 85 D. You will remember one thing, that in a downcomer, if we have a very large downcomer, the pressure drop in the downcomer will be less and your backup will be less. We want, for a good operation of a particular tray in a column, roughly about 50% depth of liquid in the downcomer. Now, a good initial guess for LW is, we already have said many times, it's about 76 to 78%. So 76% is a suggested value here, and the similar values are suggested for the other parameters like the double pass tray, what it should be and all. Now, there is a very important point here. I have to have my vapor dispersers submerged in the liquid. So, we provide a outlet wear for this, and the wear height is based on, you can see and you can add from here directly, it is a cap skirt clearance. The cap skirt clearance is this distance. The shroud ring height is this distance. The slot height is from here to here. Then we require a static seal. We decide on a static seal and we add the static seal height. So, that is the minimum height of the outlet wear that we really require. Now, when we operate, the level of the liquid will be higher and there will be a dynamic seal here, which is this distance. This is the actual level of liquid while it is operating. Typical HW is 40 to 90 millimeters for the columns above atmospheric pressure. Typically around 40 to 50 millimeter is good enough. The minimum HW that you should go for is 12 millimeters. You will notice one thing, since we often say that it will be around 40 to 50 millimeters and you will have minimum of 6 millimeters of liquid level above the wear height. So, the depth of liquid above the tray deck will be around 56 to 60 millimeters, and through which the vapor has to push through. So, very often roughly the pressure drop in case of trays we consider to be around 60 millimeter water column. It is higher than the static head definitely, because it has to pass through the vapor dispersers, during which it encounters certain pressure losses. So, your delta P across a tray will be of the order of 60 millimeter water column. Quite naturally, if you are using vacuum, you cannot afford to have such large pressure drop, and you will be using a lower height of your wear, which typically is 6 to 12 millimeters. The height over wear in this case also is given by the Francis formula with proper units that you must note from this. Corresponding to the minimum wear load, we usually try to keep at least 2 meter cube per hour per meter of wear length. So, this from, if I just know what exactly is my QL, which is my liquid flow rate, approximately I can find out the LW by considering the wear load to be around 2 meter cube per hour, and we also know that your LW is roughly around what percentage of your total tray diameter. We can have a cross check estimate of the diameter as well. Now, there is one thing which is absolutely important. The first thing is the leveling of the trays. This I had specifically said when we were generally discussing all the tray internals. Normally, the acceptable offset limit during installation is 3 millimeter. That means, the highest point of the deck to the lowest point of the deck cannot differ by an elevation difference of 3 millimeters. So, one thing is true, if I am talking about a crest level of 6 millimeters, it may have an error of about 3 millimeters. So, what you do is a minimum crest level of 10 millimeters is desirable at the lowest liquid rate for steady flow over wear. This is something very important and needs to be checked during the process of design. Obviously, the value is considerably lower in case of smaller diameter towers, where you can have much better leveling. Multi-base trays are used if your liquid flow rate over the wear during the design exceeds 5 to 8 liters per second per minute. Now, I have a question for you. Why these parameters are more important for vacuum? That means for a tower which is operating under vacuum compared to what you have in a high pressure system. The answer is obvious. It is basically the pressure drop which is at premium in case of vacuum tower, and a slight difference in level will make a difference in the total pressure drop of your column, and it will be affecting your design, and you will be spending more in creating the vacuum, and there will be a larger pressure difference between the top and the bottom of your vacuum column. With this, if we see what is further left for us, these are the items. We need to estimate the liquid gradient across the tray. This has to be done. The pressure drop across the tray has to be estimated. The downcomer backup, this we will not repeat because it has already been covered when the sieve tray design was being considered. It is the same thing here. We will talk about definitely the provision of weep holes. We had introduced you to the weep holes in one of my earlier classes in the introduction to the tower internals. What we intend to do right now is we will stop here. We will recapitulate whatever we have covered so far, and in the next class we cover these items which I have just now mentioned. Thank you.